Step 1. Consider the case A equals B. If A equals B, then the expression becomes the greatest common divisor of a to the power of n plus a, and a to the power of n plus a equals a to the power of n plus a. For the greatest common divisor of a to the power of n plus a, and a to the power of n plus a equals g to be a constant for all n greater than or equal to n. A to the power of n plus a must be a constant, since a and n are positive integers. A to the power of n plus a is constant only if a equals 1. If a equals 1, then a to the power of n plus a equals 1 to the power of n plus 1 equals 2, which is a constant. So, if a equals b equals 1, the greatest common divisor of 1 to the power of n plus 1 and 1 to the power of n plus 1 equals the greatest common divisor of 2 and 2 equals 2, which is a constant for all n greater than or equal to 1. Thus, a, b equals 1, 1 is a solution with g equals 2. Step 2. Consider the case A is not equal to b. Without loss of generality, assume A is greater than b is greater than 0. Let d equals the greatest common divisor of a to the power of n plus b, and b to the power of n plus a. Then d divides any linear combination of a to the power of n plus b, and b to the power of n plus a. Specifically, d divides 1 a to the power of n plus b minus b to the power of n plus a equals a to the power of n minus b to the power of n minus a minus b. 2 a times a to the power of n plus b minus b times b to the power of n plus a equals a to the power of n plus 1 plus ab minus b to the power of n plus 1 minus ab equals a to the power of n plus 1 minus b to the power of n plus 1. 3. b times a to the power of n plus b minus a times b to the power of n plus a equals b times a to the power of n plus b squared minus a times b to the power of n minus a squared equals ab times a to the power of n minus 1 minus b to the power of n minus 1 plus b squared minus a squared. If the greatest common divisor of a to the power of n plus b and b to the power of n plus a equals g is constant for all n greater than or equal to n, then g must divide a to the power of n plus 1 minus b to the power of n plus 1 for all n greater than or equal to n. If a is greater than b is greater than or equal to 1, then as n increases, a to the power of n plus 1 minus b to the power of n plus 1 increases. For a constant g to divide, a to the power of n plus 1 minus b to the power of n plus 1 for all n greater than or equal to n. It is highly restrictive. Let's examine the case where one of our b is 1. Let b equals 1, then we have the greatest common divisor of a to the power of n plus 1 and 1 to the power of n plus a equals the greatest common divisor of a to the power of n plus 1 and 1 plus a. Let d equals the greatest common divisor of a to the power of n plus 1 and a plus 1. Since d divides a plus 1, we can write a as congruent to minus 1 modulo d. Then, a to the power of n plus 1 is congruent to minus 1 to the power of n plus 1 modulo d. Case 2.1, n is odd. A to the power of n plus 1 is congruent to minus 1 to the power of odd plus 1 is congruent to minus 1 plus 1 is congruent to 0 modulo d. In this case, a plus 1 divides a to the power of n plus 1 when n is odd. So, if n is odd, the greatest common divisor of a to the power of n plus 1 and a plus 1 equals a plus 1. Case 2.2, n is even. A to the power of n plus 1 is congruent to minus 1. To the power of even plus 1 is congruent to 1 plus 1 is congruent to 2 modulo d. In this case, the greatest common divisor of a to the power of n plus 1 and a plus 1 equals the greatest common divisor of a plus 1 and 2. This greatest common divisor can be either 1 or 2, depending on whether a plus 1 is odd or even, i.e., whether a is even or odd. For the greatest common divisor of a to the power of n plus 1 and a plus 1 to be constant for all n greater than or equal to n, we need the greatest common divisor to be the same for both odd and even n for large n. But we found that for odd n, the greatest common divisor is a plus 1, and for even n, the greatest common divisor is the greatest common divisor of a plus 1 and 2. These two must be equal for the greatest common divisor to be constant for large n. Thus, a plus 1 equals the greatest common divisor of a plus 1 and 2. This is only possible if a plus 1 divides 2. Since a is a positive integer, a plus 1 is greater than or equal to 2. So, we must have a plus 1 equals 2, which means a equals 1. If a equals 1, then we are back to the case a equals b equals 1. If we consider the greatest common divisor of a plus 1 and 2 equals a plus 1, this means 2 is a multiple of a plus 1, but a plus 1 is a multiple of the greatest common divisor of a plus 1 and 2. For a plus 1 equals the greatest common divisor of a plus 1 and 2, it must be a plus 1 less than or equal to 2. Since a is positive integer, a plus 1 greater than or equal to 2. So, a plus 1 equals 2, a equals 1. Therefore, the only solution is when a equals b equals 1. Final answer. The final answer is the ordered pair. 1, 1, backquote, backquote, backquote.